Yep. Do you want a local recording or do you want to in their service? Probably their service. Hello? Hello? Hey. Oh, I can move that stuff. Here, let me grab that. No, you're good. You're good. Yeah.
Is this for the videoing?
Sorry?
Is this for the videoing?
Yeah. It's going to be live streamed as well as recorded.
Okay.
Good afternoon, everyone. Thank you all for coming. I wanted to take this opportunity to quickly introduce myself. My name is Philip McCoven, and I was hired a few months ago as the executive director of CUbit. It's my pleasure to restart the CUbit seminar series, which has been organized by me and Adam Kaufman and Xu Wei previously before I got here, and now starting with me. It's my great pleasure to introduce one of our sort of local heroes, Scott Diddams from down the street at NIST, to give this first kickoff seminar of the 2021 or 2022-21 fall series. So I don't know Scott very well, but looking up his CV this morning, I realized he and I share something, that we both went to very small liberal undergraduate colleges. So I went to a very small school outside of Chicago. Scott went to a very small school outside of Minneapolis, St. Paul. After that, he went down to got a PhD from the University of New Mexico in Albuquerque, and then actually came and did a postdoc at JILA before starting his career at NIST. So Scott has many awards and many things, recognitions for, including the IEEE Robbie Award, a silver prize from the Department of Commerce, and a gold prize from the Department of Commerce. He's a fellow of the OSA and ATS, and I think he did much of the foundational work and early work of frequency cones, which I think he's talking about today. So I'm very much looking forward to seeing it. So without further ado, Scott.
For the invitation and a kind introduction. I get a little reverb here. Can you still hear me okay then? Okay, great. So yeah, it's a pleasure to be here today. What a novelty to stand in front of an audience in real person. I think for the past year and a half or so, I've only given talks remotely. So it's great to see real faces and lots of friends and new people who I look forward to maybe getting to know better. So I'm going to tell you today about optical frequency cones, and I have to confess that giving a CUbit seminar, I felt a little bit under pressure to get 2.0 in there. Honestly speaking, frequency cones haven't fully come 2.0 from the quantum sense of the word, but there's certainly been many variations, and versions of frequency combs. We definitely went through 0, 1, 2, 3, 4, 5. Who knows? Maybe we're up to 10. And so I'll recap a little bit of that story for you and tell you a little bit about some of the most recent advances in the field. And then towards the end, I'll touch on where we might hope to go and some ideas, directions that I think could be interesting when we think more about truly quantum 2.0 systems. So if you shift the decimal point over 1, we can talk about frequency combs at 20. So it was about 2 decades ago that when I was a postdoc in the basement of Gilla, working with Jan Hall, that we came upon something special, and that was this first demonstration of optical frequency combs and the ability of them to phase-coherently unite the electromagnetic spectrum. These were some of the papers that got published at that time, and these 2 gentlemen, who you probably know, were already very famous, had a spectacular careers worth of achievements already, but it seemed this frequency comb thing pushed it over the edge a little bit, and it was noted in the 2005 Nobel Prize as part of the reason that they got it. So it has been something that completely changed my life to work with someone like Jan Hall and you know, the other people around him. So just about 22 years ago, October 6, 1999, postdoc David Jones and I, David worked with Steve Cundiff, I worked with Jan Hall. We got these data in the basement of Gilla. It was interesting, and I'll explain more about what those data mean, but that was our first self-referencing signal. This is really the linchpin in building a comb that operates like a clockwork. These were the very first data that showed that on October 6, 1999. Interestingly enough, a key technology that made that possible showed up in the mail only 2 days before. The story of frequency combs is really the opposite of Murphy's law. At least in the early days, everything that could go right went right. And the field progressed very rapidly. Here's some handwritten notes from Jan. I think it says super Loctite pulse envelope carrier phase controller, the femtosecond synchronizer. Jan was an integral part in all of our discoveries and in guiding us. And of course, in doing one of his favorite hobbies, building really cool circuits that would control the frequency comb for us. So that kind of revolution led to this picture of what a frequency comb is. It's really an optical clockwork that connects the entire electromagnetic spectrum, from RF fields all the way to optical fields. And this picture of gears is actually a really handy one that I like to hold in my own mind when I talk about frequency combs. The comb, the big central gear, acts as simultaneously as a divider, which would take optical frequencies in, divide down, microwave frequencies out. It can act as a multiplier, take microwave frequencies in, multiply up, and then have these optical frequencies out, the little cogs there, turning very quickly. And then the optical spectrum, you have to remember, is hundreds of terahertz in bandwidth. And so to traverse that spectrum, the frequency comb can also be used to, say, take violet light and convert it to red light or green light or any color that you would want. And these modes of operation all happen simultaneously. You can think of this thing as just a wheel spinning there all on its own. And then you, as the user, would come up and would enmesh the gear, the frequency that you're interested in, with this set of spinning gears and generate another frequency that you might like. So when you think about what this accomplished, you can take still a further step back, and it's interesting to notice that Maxwell's equations govern everything we know about electricity and magnetism. But if you look at the properties of different regions of the spectrum, they're very different, and in particular, the devices or the technologies that have arrived or that have evolved around different regions can be very different. For example, if we think about optics, very high frequencies, very extreme resolution, low loss, extreme bandwidths. This is the regime of future clocks, and maybe it's best personified or exemplified by fiber communications. Everything that, in fact, you people out there, you know, my voice is going on light somewhere and making it out to you in some way. Electronics, on the other hand, radio frequencies, microwave frequencies, there's mature synthesis, very complex modulation, extreme integration. It's the place where the SI second still lives, cesium clocks, and maybe it's best exemplified by radio communications, navigation, the things that you hold in your hand all day long, your phone, right? It's all RF electronics in the way that communicates with the outside world. But for many, many decades, there was no coherent connection between these two regimes of the electromagnetic spectrum. And the frequency cone made that connection, a phase coherent connection, for the first time. And this is a picture. You could read this paper if you're interested in much of what I say in the talk, at least the historical parts are in that paper there. But if you trace in time along the bottom axis and frequency on the vertical axis here, the RF world has a much longer history. And at least in terms of human-controlled coherent signals, it all started with Hertz back in the late 1800s, and then it blossomed into radio frequencies, microwaves, radar communications. Optics had its similar beginning with the invention of the laser in the 1960s, and yet for 40 years or so, there was no way to phase coherently bridge this gap of many orders of magnitude between them. And that's in fact what the frequency cone did. And so it unified the electromagnetic spectrum and thereby opened up the possibility to share perhaps the best qualities of the RF with the optical and the optical with the RF. So we can seamlessly move between these two domains now. And that's really the main story of a frequency cone. Okay, so that's a brief introduction, and I'm going to have to move along quickly. I told we get kicked out at 5 p.m. and I got a lot to cover. So in light of that, I think I'll focus on these 4 points. I realize that some of you, you come from a diverse background, and so I wanted to give a little bit of introduction as to how a frequency cone actually works. It's of course not a set of gears. What does it really do, and how does it really do that? I'll tell you a little bit about some of the common platforms. I'll spend one of the most exciting parts of my work is finding new applications for frequency cones, and then at the end I'll speculate maybe a little bit on what the future holds for frequency cones. So frequency cones are really a type of laser that supports multiple modes of light. Okay, so that's the different colors that you see here, bouncing back and forth between the two mirrors I show there. And these modes of light are mode locked or phase locked together, such that each round trip in the cavity, they actually add up to form a short pulse. This is the key ingredient, phase locking or mode locking, that all cones have, a means to enforce phase synchronization between the modes. And this is done with different techniques, but that's really the key piece. And you need, in addition to some sort of a laser or cavity that supports those kind of modes, you need this cavity to reduce high frequency noise. And that's another key feature of frequency cones. But we see already, maybe just in this snapshot, some possibility of connecting those optical waves to a microwave field, which is the rate at which the light circulates in the cavity. Okay, so let me try and explain a little bit better how that actually works. And it's helpful to back all the way up to what we call a continuous wave laser. So we're going to progress from a CW laser to a cone. So a continuous wave laser just emits what looks like a sine wave, an electromagnetic wave, with period t, that's the inverse of the frequency. And if you took the Fourier transform of that wave, it would be like a delta function in the frequency domain, okay? Now imagine if you had a modulator that could turn on and off that CW wave at a very precise rate. In fact, it could turn it on and off, in this case, every 10 cycles of the CW wave. Okay, so we have this modulator, it defines this envelope, looks Gaussian-like, wouldn't have to be Gaussian, but anyway, it turns it on and off at every 10 cycles. The first thing that you would note is that now your single frequency now assumes a cone of frequencies. Okay, and the very special thing happens here is actually if you can establish this pure harmonic relationship between the modulation frequency and the underlying carrier frequency, you can write any frequency in that cone as just an integer times the mode spacing, or the inverse, or the rate at which you turn it on and off. Okay, and if that was, and that's actually a perfect frequency divider, a perfect frequency counter. You see the connection between optical frequencies and something that is a microwave frequency there very easily. Of course, at 500 terahertz, you aren't going to find a modulator that can turn things on and off at 10 cycles, but for this explanation, that's exactly what you would need to make a perfect divider. And if that were all it was, the story would have been over in 1960 when people developed modulators and mode lock lasers for the first time. But there was a twist. And this twist was that very simple one, that inside a laser cavity, that these modulations, or the pulses, they travel at a different velocity than the carrier waves. And that means that in each, from pulse to pulse, then, the modulation slips. The group velocity is a little slower than phase velocity, so as I drew it here, there's a small offset from pulse to pulse. Okay, and this is actually the problem that hung up frequency cone for like 30 years. And the implication of that in the frequency domain is that now these modes are shifted a little bit from being pure harmonics by a frequency we call the offset frequency. And you might think, well, gee, that screws up the entire game. We're never going to be able to recover from that, because how am I going to measure this tiny little phase shift in the time domain and recover what fraction of the cycle there was this slippage by? But the real breakthrough in understanding was that that small fraction of a cycle shows up as a frequency itself. And we can measure frequencies very well. And so with a simple interferometer like this is what we call a self-referencing interferometer. That was that first bit of data I showed you on the very early slide. This is what was constructed, was an interferometer that takes high frequency portions or low frequency portions of the cone, frequency doubles them and interferes them with low frequency, or excuse me, the high frequency portions. And if you do the math, I can't quite say it, but I think I could do the math. And you subtract and heterodyne these two fields, you end up with this offset frequency exactly. So in the frequency domain, we're able to measure this fraction of slippage from pulse to pulse of the carrier envelope phase. And this was really the breakthrough that enmeshes those entire gears together and makes it possible to build something that is truly a universal optical to microwave converter. The little piece of the equipment that showed up in the mail on October 4th was a piece of this, what Jan called the seriously nonlinear fiber. This fiber was a very special type of fiber that was made at Bell Labs. It has air holes around the central core of the fiber where the light was guided. This is called a microstructured fiber. It confined the light very tightly. It altered the dispersion properties of the fiber of the waveguide, and that allowed one to generate this supercontinuum, this rainbow of light that goes from blue to red, so we could perform that offset frequency measurement. Once you've measured the offset frequency, then what we have to do is control the one other degree of freedom of the cone, and that's what we call the mode spacing. And that was actually much easier. We can either measure it directly, compare it to a microwave clock, but the better way to do it is to use an optical reference. Now, the very most stable electromagnetic oscillators of any kind are those that exist in the optical domain. This is what I mean, is that like a cone allows us, you couldn't do this before, but now with the cone, we can share these unique properties of an optical oscillator, and we can control the cone with that, and thereby control this mode spacing or the repetition rate, the rate at which the pulses come out relative to this optical signal. And you see there's just a few RF constants in there and an integer n, which is the mode number. Optics wins in this game. The state of the art for optical references is 2-3 orders of magnitude better than microwave references. So if you really want to make the best optical clock, this is what you do. You do the optics, you do the spectroscopy in the optical domain, you use the cone to divide down. I won't say too much about this, but a big question early on was how good were the gears? Like, could these really be perfect gears? Like, how could anything be good, that good? Well, it turned out myself and others invested a lot of time trying to answer that question. And the number now sits at about part 10 to the minus 21, that this simple equation that relates the optical frequency to the microwave frequencies is true at that level. And there's maybe another way you can ask that question. You can say, well, yeah, I know that on average there's a certain number of teeth, but maybe they slip every once in a while. This is a question of phase noise, and our colleague here at CU Physics, Thomas Shibley, I think has done the best test of that to show that actually these gears, if you want to think of the gears as being optical cycles, you can subdivide one of those gear teeth by about a 1,000 down to kind of milliradian of 10 attosecond level. So this is really, as far as we can tell, a perfect gearbox for doing these kind of measurements. Okay, so that's a little bit about how frequency combs work, what enables them to do this optical microwave conversion so efficiently. Now I'll tell you a little bit about some of the common frequency comb platforms. And this is really where actually in the past, I'd say 5 to 10 years, there's been a lot of action on trying to make frequency combs that were more robust, more user-friendly, capable of doing more and more measurements. So basically it comes down to 3 different platforms, and I'll say a little bit about each of these. There are mode lock lasers. This was the original type of frequency comb. And here it's depicted as maybe the most modern version, which is a fiber laser. The light doesn't bounce between mirrors, but it circulates in optical fiber through a cavity. There's very interesting combs we call electro-optic combs. And these are combs that the mode locking mechanism is enforced by a microwave field that drives an electro-optic crystal. And we might put them between mirrors. I think maybe you remember I said you often need mirrors to reduce the high frequency noise. Turns out that works quite well. One of the most exciting areas of research is in devices we call microcombs. And these are frequency combs that can be printed on a chip, similar to electronic circuits. Okay, and except they're circuits that are dielectrics, so that light can propagate inside a small waveguide on a chip. And they use 4-wave mixing, a nonlinear process, the Kerr effect, for introducing this phase synchronization between the modes. So I give some of the parameters there at the right, and I'll walk through a few of these different systems. The erbium fiber combs are the most mature, and just as an example, I hold out the work of my colleagues at NIST, Laura Sinclair, Ian Coddington, Nate Newberry, and colleagues who built these kinds of devices. And in fact, former postdoc from their group, Greg Rieker, faculty member here now, has a company that he spun off that takes those same frequency combs out into the field and uses them to measure emissions from, or leaks from oil fields. So these are devices that can really, you can buy them, you could take them just about anywhere. A company in Europe, Menlo Systems, is packaging frequency combs so far on sounding rockets, touching kind of the envelope of space. But I think it's not too much longer before there will be real optical clocks and frequency combs with them in space. So this is a very mature platform and applicable to many different types of measurements. These ones are, as I show you here, are perhaps some examples of really out in the field, but these are devices we use in our lab every day. And in fact, I really like this technology and try to build almost everything off of it. So starting with erbium fiber frequency combs, that's this 1.5 micron mode lock laser. It leverages all the advanced technology of telecommunications. And so they're cheap, they're inexpensive, they're very robust. Then we can play some nonlinear optics. I don't think I'll go into describing that, but using that, we can make these things that look like delta functions in the time domain. So there's kind of these 2 sides of a shiny frequency comb coin, if you will. And you can look at one side and you can see that cone picture in the frequency domain. It looks like delta functions in the frequency domain. You flip it over, you look on the other side, and it's delta functions in the time domain. It's a train of ultra short optical pulses. So we like constructing frequency combs in this way, and that turns out to be very useful because it allows us that those delta functions in the time domain have tremendous peak power. And that allows us to drive optical nonlinearities in different materials to produce spectra like this. A frequency comb in this case that spans about 6 octaves from down in UV 350 nanometers up to beyond 22 microns. And this is done by taking one of those short pulses I showed on the previous slide, and in this case putting it into one type of crystal. And in fact, the bandwidth is so great that it's hard to do that all in one medium because you can't find dielectrics that have transparency over that pull range. So this lithium niobate crystal allows us to go down to these short wavelengths, and different crystals allow us to cover the long wavelengths. And these are envelopes of the spectrum that we show. So for those of you who maybe haven't seen this before, but if you could zoom in, and in fact we can zoom in, you can see that under this envelope there's this dense array of comb teeth. These teeth are in this case spaced by 100 megahertz. A new advance in this field is to move away from those types of microstructured fibers I told you, and to employ nonlinear nanophotonics. And these are some examples of devices that I've been involved in working with colleagues Scott Papp, Rich Mirren at NIST, Kerry Bahala at Caltech, and many different platforms. But the key feature here, if you want to just focus on one, is that by patterning optical waveguides at the nanoscale, we can confine light very tightly. So that means that the intensity of those fields can be quite high. That enables the nonlinear optics to turn on very easily. It also enables us to adjust the dispersive properties of the waveguide, so we can change the distribution of the light that's generated in these kind of waveguides. And most importantly, it pushes down kind of the energy scale from the nanojoule region to the picojoule region. So this turns out to be very useful if you want to, say, make frequency cones that are very small, robust, and energy efficient. One of my favorite devices here is lithium niobate again. And these are some examples from postdoc Sunhan Wu's work recently, together with a group at Caltech, where we're making chirped lithium niobate waveguides. And here again, you can see extremely broad spectra. This time we're plotting in terahertz. So the spectra goes all the way out almost to 100 terahertz, 3 microns, and down into the UV. 850 terahertz is again about 350 nanometers. You see the little movie running here shows our simulations. We have the tools to model these things, to design them. And it's I would say, for quantum engineering, this is like the machine shop of the future. Is you want to be able to pattern and make these types of devices on a chip to tailor light, broadcast it to wherever you want. So that's tools that we use with mode lock laser cones. We can use that nanophotonics, of course, with other kinds of cones. A very interesting comb, in fact, one of the very early cones, even before there were the mode lock laser cones, were electro-optic cones. And these are interesting because you can generate frequency cones without any intrinsic mode locking mechanism itself. You send in CW light, you drive an electro-optic medium with an RF field, and that makes sidebands. The process can cascade, and you can generate very broad cones like this. Here you see the blue region looks practically filled in, but if you zoom in, there's a cone tooth there every 20 gigahertz. You can make short pulses out of those, and you can also drive optical nonlinearities to spectrally expand the cones. So this is a Kuroki type cone, we call that. That was actually one of the first cones that I worked on in Jan's lab. More recently, through the advances, again, in telecommunications technologies, there's been very efficient phase and intensity modulators that are now available. And so we can take a CW laser, pass it through these modulators, drive them with microwave frequencies, and directly produce cones like this. And you see the modulated cone teeth there. The depth of visibility there is given by the instrument that we use to measure them, not by the true line width of the cone teeth. They're, perfect signal to noise if you were to see it with a high resolution instrument. But now we can take this cone and reshape it into a short pulse, and again drive nonlinearities and nanophotonics. There's a little nanophotonic chip you see, and these are simulations of the measurements that we were able to do. And you can again take this narrowband cone and blow it up to octave span. This self-referencing step can be done, and one can have it. Starting is quite interesting with the CW laser and a microwave frequency. You can generate a phase-coherent cone. And by the way, this was work done with my colleague Scott Papp, and David Carlson is a postdoc who was working with us at that time. So I already mentioned that one of the most exciting areas of frequency cones is this area we call microcones. The vision here, the dream here is you just have to look at these devices and you can catch on pretty quickly that these are like circuits for light. They're printed on silicon. And so you could imagine building cones like you build computer chips. The process that makes these types of frequency cones is one called four-wave mixing, where you would again inject some continuous wave light, so one frequency of light into a resonator. You could think of this resonator here. A little bit of the light gets coupled in, circulates around and around. It builds up the intensity, and when the intensity becomes high enough, you can have this four-wave mixing process turn on, where two photons of, say, the pump color scatter or break apart, if you will, into one that's slightly higher frequency and one that's lower frequency, and populate two modes in the cavity, and then this process can cascade. So some of the advantages this platform provides here are shown here, and I would say chief among those is the integration on the chip. There's, as much as there's been interesting device physics and understanding of devices I showed on the previous slide, the physics that governs the generation of these microcombs is very beautiful. It's based on a nonlinear Schrodinger equation and the Kerr effect balanced by dispersion. In this case, it's a forced or driven damped system. It's called the Lefebvre equation. That's a version of the nonlinear Schrodinger equation. It has these named terms in it that you see there. And a very beautiful outcome of this is that you can produce solitons inside these resonators, these micro-resonators. So you see in the frequency domain, the cone structure would have an envelope of a hyperbolic secant. In the time domain, it's also a hyperbolic secant pulse that surfs on the background of that continuous wave light that originally fed the energy into the cone. The engineering one can do with these devices is quite powerful, and it's shown in this work, which again was done with Scott Papp. Travis Bryles was a postdoc at that time who led this paper. And what you see is that by changing the dimensions of the waveguide, if you look here in the upper right, the width of the waveguide or the diameter of the waveguide, you can change the spectrum. And so what's being changed here is the ring width, this W parameter, and you can see you can push energy in the wings of the cone along these dashed diagonals shown here. And that allows one to position energy at frequencies that are roughly an octave separated. So this could be a very efficient way for self-referencing these cones. And as you see, there can be quite good agreement between theory and experiment, and that theory is coming from that Lefebvre equation I showed on the previous slide. So those are a description of some of the main cone platforms, and I would say there I went through 3 or 4 generations, so 2, 3, 4.0 of different devices for generating cones, and that continues to be an active area of research for many people in the field. So let me talk a little bit about what we're using frequency cones for. I like this picture of an evolving application tree, and I've made a few versions of this. I enjoy, maybe as you gathered, I enjoy kind of physical pictures that help me understand, like not only how the technology works, like gears, but how it spreads and impacts other things. And what we found is that, starting from kind of a self-reference frequency cone, there were many applications that would go up, but just like the blood flowing through your body or the sap in a tree, the water, the energy flows up from the roots, the nutrients flow down from the leaves, and there's kind of this symbiotic relationship between technology driving the applications and applications driving the technology. And this has been true throughout the history of frequency cones. So frequency cones impact many applications, and that's what these different branches are, but there's some that are absolutely critical. For example, if you want to make an optical clock, if this is a quantum technology that we believe we're going to have widespread in our world in the future, you need a frequency cone to do that. Frequency cones can generate now the very lowest microwave, the lowest noise microwave signals, very broadband sensitive spectroscopy. I'll tell you a little bit about that. We're using them to find Earth-like exoplanets. I'll share a little bit like that. And a huge area that I'm not going to talk about, but there's folks here at Gillette, for example, doing work like that, is the dependence of the fields of very short pulses on this carrier envelope phase. It turns out to be very important in generating like isolated attosonic pulses. So let me just tell you in one slide about clocks. The best clocks in the world are here in Boulder, if you didn't know that. And they're connected by fiber links between NIST and Gillette, and also free space links. And in that clock network, you can see on this picture, at least 3 frequency cones. Actually, if you take into account the free space links, there's a couple more frequency cones at the ends of those links. So these are kind of like synthesizers in networks. You think about a communications network, you would have different devices up and down conversion at different places in your network. That's exactly how the frequency cones are functioning in this network. I won't say anything about it. You could read in this paper that came out last year from our Bacon team, and that's a big team. I have to say I played a small part in that, but a wonderful group of people to work with that constructed this network, and that was used in things like searches for dark matter, tests of fundamental physics, relativistic geodesy, and ultimately it's going to be play an important role in the redefinition of the Sept. Another type of clock that some of us have been involved in making is chip scale clocks. So these are clocks that don't measure time in 18 digits like the ones on the previous slide do, but maybe in 12 digits, but they have the potential of sitting inside your cell phone someday. And these could be atomically referenced clocks. In this case, maybe rubidium is a good atom to build such clocks on. And then we use, just like I described before, we use frequency combs as gears to divide down that 385 terahertz transition down to a countable output at 22 gigahertz. And this picture, if you are this type of data, if you're not familiar with us, that's an Allen deviation. It shows how the output, the stability of this rubidium 2 photon, that's an optical transition in that clock, how it averages or how the precision improves with averaging time. So this had all the key components for clock on the chip. I'd have to say that all of them weren't integrated together. There's still a lot of work to be done in integrating devices together. So you could really have one device that would fit inside your cell phone. I'll say a little bit more about that. But this was done again in collaboration with many people, including John Kitching and Matt Hummon, and again, my colleague Scott Papp at NIST. So let me say just a word about spectroscopy and sensing with combs. This is another very important application where you can think of what we do is we just take frequency combs, send them through something that we might want to measure. Let's think of it in gas phase. It's easiest to do. And then on the backside, we would have some spectrometers. So in this process, maybe a molecular absorption profile gets its fingerprint imprinted on those cone modes. So there would be some absorption of the different teeth. And then you would, if you could read that out, you'd be able to know what the frequency comb passed through. And so an advantage of doing that with a comb is you know exactly where those teeth are. Okay, so you have like built-in frequency calibration. You can also make them very broadband. They're much brighter than the light you would have, say, from a thermal source. One challenge, however, is reading out those teeth, right? You got the information on, what kind of spectrometer allows you to get that information off? And I'll say a word about that in another slide, but I would just say that there really is world-leading work going on here at CU and NIST, and I list a few of the players there. So how do we get that information out of a cone? Okay, and I like to say, well, it's all there, we just have to listen to the molecules. And so one way of thinking of this is if you would excite a molecule with a short pulse, so this is that other side of the coin, of the frequency cone, we hit the molecule with pulses of light. The molecule vibrates, okay, and there's some emission of that vibrating energy. I show it here as a little blue trace. Well, you might put that into a Fourier transform spectrometer or a gradient spectrometer. That'd be one way to analyze it. But what we do, a common technique, is to use a second frequency cone to read it out. And that frequency cone then gets delayed automatically, and I'll explain that in just a minute, with respect to the first, to the emitted light. And you can use heterodyne detection to read it out. And the key feature is that these two cone pulses are phase locked together, okay? So you use excitation from one cone, you read it out with a different frequency cone, and they're at slightly different rates the pulses come. So it's like what would you say, like a sampling oscilloscope type effect, where one of them is constantly walking by the other one and reading out the information imprinted on that blue light with the red pulse here. This leads to capability for very high speed, very broad bandwidth measurements, no mechanical parts, so you aren't translating the stage like in a Fourier transform spectrometer. So we can even dream of data rates in excess of a megahertz. We've implemented this in a couple different ways, and this is one example from my lab. There's many other excellent examples around town. But here we actually generate mid-infrared light with one frequency cone, and we read it out in a nonlinear fashion. with a near-infrared cone. And we call this electric field sampling. And I'll say a little bit more about this later in the talk. But the thing that's kind of interesting about this is we can use those delta function pulses again as kind of digital samplers and to read out this longer wavelength mid-infrared light. And while it might be easiest to think of it as a digital sampler in the time domain, it has a complete analogous description in the frequency domain as the interference between up-converted frequency cone and the reference cone. But that allows us to do spectroscopy like this, so that information, light got imprinted on a mid-infrared field by going through an ammonia cell. And this is what the spectrum looks like in the reference. We remove the reference and we can get kind of a baseline-free measurement, high resolution of ammonia. And this is extremely broad, over octave bandwidths in the mid-infrared, okay? And extremely high resolution. Each blue dot here on this bottom curve, it represents the spectrum achieved by a single tooth. So this shows you that problem I presented earlier, where we can get the information on the cone teeth, we can indeed read it out again at cone tooth resolution. So what other types of measurements could a frequency cone enable in spectroscopy that cannot be done with other techniques? And together with Greg Rieker and Nazanin Khokhovi, we were thinking about this and came up with this type of way of parameterizing spectroscopy measurements, where on one axis you might have optical bandwidth, on the other axis you would have spectral acquisition rate. So think of your favorite type of spectroscopy experiment. Maybe it's a scanning CW laser. Well, you know that a CW laser can scan very rapidly over a small distance, but if you try to extend the spectral range, then it becomes harder and harder to scan it fast. Or you have to slow it down a lot. Fourier transform spectrometers have tremendous spectral bandwidth, but you got to wait for the darn cart to move back and forth, right? So you're taking data at kind of 1 second rates. What we are interested in doing is pushing into this corner, which I think is a very challenging corner to get to. So some of our present work is here. Our future work is that light purple place up in the top corner. How are we going to do that? Well, it turns out that we just need to go to higher speed devices. So this is our first effort at this with frequency cones that operate not at 100 megahertz, like the example I showed before, but 1 gigahertz. We're building 2 of those to be a transportable instrument. And Greg in particular is interested in chemical dynamics, high-speed combustion events. I'm interested in high-speed hyperspectral imaging. I'll say a word about that in the next slide. But we already have kind of the first data point in that we can make infrared light over about 1,000 inverse centimeters or 30 terahertz, and that puts us right at this yellow star here, far in excess of what's easily achieved with other techniques. If we want to go to the future, we're going to have to up this rate, not from a gigahertz, but maybe up to 10 gigahertz. And that would be the path to getting, spectral acquisition in excess of megahertz rates over hundreds of terahertz of bandwidth. So that would be completely uncharted territory, and I'm not aware of other spectrometers that can do that with high resolution. So one of the reasons I'm excited to do that is to do infrared microscopy. And the infrared region is very useful for doing all kinds of spectroscopy because it's the fingerprint region. It's the region that tells you the structure of molecules. So this is a simple experiment we did a few years ago where it wasn't a very exciting molecule we were looking at. It was a polymer SU8, which is a photopolymer that is used in lithography, and we could pattern it onto a silicon substrate and then look at it and then measure the spectrum, okay? And what you're seeing here is the blue curve is like the average spectrum over all these places, the little lighter blue in the image where there's SU8. The red is at a particular spot, okay? So that just shows that we could do spatially sensitive hyperspectral microscopy. And SU8 isn't super exciting, but where we really want to go with that is to look at biomaterials or bio stuff that matters, such as proteins. The structure of proteins, as observed in these bands, they're called the amide bands, tell something about the way proteins fold up or unfold. And that, in fact, can be an indicator of whether proteins are healthy or not, diseased or not. So this is an interesting direction we're interested in pursuing, and I know there's others around here at the university who are looking at at similar things. As a last example, I want to just tell you for a few minutes about one of my favorite topics or applications of frequency cone, and that is to try to address big questions in astrophysics. And here's a few that I'm aware of. How do planets form and evolve? How diverse are planetary systems? Is Earth unique? So far, we only know that there's us. There's only one Earth-Sun analog. Is there another one out there? Seems like there should be, but we haven't found it. And ultimately, is there life elsewhere? So one of the techniques that's used to find exoplanets, to study planetary systems, is this radial velocity technique. And Mayor and Culot won the Nobel Prize in 2019 for their discovery of an exoplanet circling an Earth-like star using this technique. And here you can see this cartoon tells you how this works, and it's exaggerated. The planet is actually tiny, tiny. You can't see the planet with the telescope. The star is far too bright. But what you can see is the spectrum of the star. And as the planet goes around, it tugs on the star ever so gently to and fro, and you measure those small spectral shifts. If you wanted to find an Earth-Sun analog, the Doppler shift is really tiny, 10 centimeters per second. You're looking at a star many, many light years from us, and you're trying to tell whether it's moving away from us or back towards us at 10 centimeters per second, and you want to measure that over a period of a year or multiple years, you're going to need a frequency cone to do that. And that's what we've been doing with colleagues at Penn State University. Surab Mahadevan is a really wonderful collaborator on this. We built a frequency cone that is combined together with a spectrograph that they built, and it sits in the basement of this telescope at the McDonald Observatory in Southwest Texas, the Hobby Eberly telescope. The frequency cone acts just like a ruler of light against which those dark Fraunhofer-like lines of the star are measured. There's a picture of the telescope dome at night. The stars, this particular spectrograph was made to look at what are called M dwarfs, cool red stars. And in fact, the stars that our astronomer colleagues look at, you would not see them in the sky with your naked eye. They're very dim stars, okay? But the peak of the black body spectrum is in the range of 3,000 Kelvin as opposed to 6,000 Kelvin for our sun. Here's how the experiment works. We combine some of those tools I described to you earlier. Electro-optic frequency cones make this broad spectrum that's done with supercontinuum in nanophotonic waveguide. And this is the spectra that the instrument measures, the habitable zone planet finder spectrograph measures. You read this thing kind of like a book from left to right, from top to bottom. You go from 800 nanometers down to 1300 nanometers. It's called a shellogram from a cross disperser. And if you zoom in here, you see, you can rapidly or easily see that the idea here is that you'd have the star spectrum there, kind of a continuous spectrum, a few dark spots in it, and underneath you have the little tick marks of our frequency cone. So one of the reasons I like astronomers is they're definitely not afraid of hard problems. I know there's lots of hard problems people are solving every day, but these don't really captivate me. If you look at what we're trying to do is 1 pixel in this spectrograph corresponds to about 1 gigahertz of resolution. You need to split the pixel by about a part 10 to the 4. That corresponds to about a few lattice sites of the atoms. This is an infrared detector, mercury telluride, but if it was a CCD, it'd be silicon. So you're trying to see that spectrum move by about 5 lattice sites on a CCD-like device. So that's really hard. And the only way you can do that is like everything has to be right. You can't, and the frequency cone is an integral part of it, but it's only part of it. And so it's a really challenging instrumental problem. Here's some examples of recent results, and this one is very fresh off the press. And you see the types of signals that we're looking for. So here on the left, you see the period of a planet going around a star and sitting at different points, or the measurements. If you phase them all up, so now we're looking at one period of the rotation of the planet around the star, you see they all line up on something that looks kind of like a sinusoidal curve here. Note that the axis here is just meters per second. We're not at 10 centimeters per second with this device. I don't think we ever will be, or this spectrograph It wasn't intended to reach those levels yet, and it's also a near infrared spectrograph. But this was evidence of a 2.5 times Earth mass planet in a 2-day orbit around this star, about 26 light years from the Earth. One thing that was interesting science that came out of this is actually this planet was first observed in the radio frequency domain. My understanding is the planet is close enough that it interacts with the magnetic field of the star and produces radio frequencies at like 150 megahertz that then are modulated as the planet goes around the star. So this is the first confirmation that they're in fact by a secondary technique that there really was a planet around the star. Another example is really a fascinating one. Barnard's star is a star that has been studied for well over 100 years, I think. People have thought there were planets around it, then it was not planets around it. It's an old M dwarf, it's very stable, so we thought we would use it to test out our technique. And in fact, lots of other astronomers were looking at this same star. These are all their measurements. Our measurements are these last ones here. So this comes after about 3.5 years of continuous operation. And just when we went to publish our first result, the folks who had made these data thought they saw a planet. Our measurements, our team's measurements, I'm using our generously there, I didn't do the analysis, but ruled out this candidate planet. So in this case, in fact, at least to our best of our measurement, Barnard's star does not have a planet. So we killed the planet instead of found one. But anyway, this is something that you can only do. You see this axis is measured in days, thousands of days, okay? So you really need a quantum reference system here if you're going to make measurements over long periods of time that are going to be sensitive. So I think that's really a powerful statement for using something like a frequency phone. Okay, I'm not doing too bad for time. I'll come to the last topic here, which is, what does the future hold for frequency cones? And it's always dangerous to look into the tea leaves and try and read what the future might have for you. But I'll not step out onto too shaky a ground. So let's just go back to that picture. That picture, if you read it in detail, or you got to go get the journal article and look at it. There are a few things here in the future. The dashed line was the present in 2020. These are some ideas that I think are going to be quite important for frequency cones, cones at extreme wavelengths, X-ray or IR. I think there's efforts here in Boulder on trying to find a very curious transition in a thorium ion to try and build a nuclear optical clock. No one's yet found that transition. In fact, there's not a laser that exists there to probe it. And so it's going to be a frequency cone that one day will measure that transition. I think there will be cones in extreme environments. We already saw a few extreme ones. Oil fields aren't the friendliest places. But I think in space is one. And I would love to see, I think Boulder and the folks here in Boulder, not only between places like NIST, GILA, engineering, have all the right people to lead efforts to put these kind of technologies in space, where I think they would have an amazing impact. I think there's going to be ubiquitous cones, I call them, and that's CMOS integrated cones. CMOS is complementary metal on oxides. I don't even know exactly what it means, but CMOS is like how you make integrated circuits, okay? And so the vision is that one day we're going to be able to make frequency cones using that same technology, and they're not going to cost hundreds of thousands of dollars, not tens. They're going to be cheap, And so I think that's an area that is coming. Quantum cones, and I say quantum cones and measurements. This is an area that I personally haven't taken a full step into, but I'll share with you a few ideas about what I see there. Let me talk about the ubiquitous cones first. Optical frequency synthesis on a chip. This was an experiment, again, with Scott Pack that we did this, and a team led by John Bowers at UC Santa Barbara, where we combined these different chips to make an optical frequency synthesizer, maybe not on a chip, but with chips, let's say. So there were these different frequency cones in there. There was integrated tunable lasers. There was the self-referencing piece. So everything was exactly like the gears I showed you before, with impressive performance. And what you can see here, this cartoon that's running, is that The output of this synthesizer is being stepped by a few hundred kilohertz, step and stop, step and stop, step and stop. So each dot there is saying, okay, I want the laser to go to this frequency and stay there for 10 milliseconds. I want to jump it to another frequency and stay there for 10 milliseconds. And if we do that over time, we can spell out the word mix. But if you looked at what that experiment actually looked like, here is a nice photo. The frequency cone or piece sat down here, okay, in between all of these observation and coupling stages. There's an image, a little bit of scattered light, the light going around the cone circumference. Here's the beautiful spectrum. I showed you an example of that earlier, and the key self-referencing beat note is up above there, but it was an optical table. And in fact, there was another optical table behind the photographer that some other parts of the experiment sat on. So what's really needed in this area is, to keep the micro in microcone. Now, the hardest thing in this field right now is self-referencing a microcone in a package that's commensurate with micro. And there's a lot of people working on this. It's a really challenging and hard and exciting problem. And I do believe it's going to happen. And not before, certainly before I retire or quit, but it's imminent. And because there's so many wonderful ideas. And here's one, again, my colleague Scott Pack, working on parts of those devices. So I said there's three things that would be needed: octave spanning cones at low power and low repetition rates. Okay, integrated pump lasers and self-referencing on the chip. So here's an example of at least parts of 1 and 3, where a simple laser has been put together with a silicon nitride microresonator. There's an optical fiber output. There's electrical signals coming in that provide energy to that laser. And you're able to make these kind of spectra where one can get octave spanning spectra under different conditions. What's missing here is these spectra are still at rather high repetition rates at about 1 terahertz. And that's hard to count. You'd like the frequency cone to divide all the way down to kind of tens of gigahertz range, which would be easy to count. The challenge there is that energy is conserved in these systems. And if you put in 30 milliwatts, as shown here, and you say, well, I'm going to divide that 30 milliwatts among 100 teeth, then it works. But if you have to divide that 30 milliwatts among 1,000 teeth, it becomes a harder problem. So that's something that the community continues to work on. But I think it's really an outstanding problem and one that will happen. How that could look, and this is the work of John Bowers at Santa Barbara, where even without everything working, it's kind of interesting to try and build the house. The plumbing wasn't 100% in place, but to imagine how such a device could sit on a 3-centimeter substrate, and then in a future version in a more packaged environment with the electronics on top is something like this. And this is a hard problem called heterogeneous integration, because everything isn't made out of the same material. Like a computer chip, it's all silicon. But here you might have 3-5 semiconductors that are used for the lasers. You have a different material used for the microresonator. You have photodetectors that are a different material. And then on top of that, you have the CMOS electronics. And it all has to be integrated together in a sensible way. And so that's a real quantum engineering challenge, I would say, because it's not just building it. It's understanding like every piece of the problem that goes into solving that integration aspect. I'll just quickly say something about quantum frequency cones. I'm not the right person to be giving a talk about quantum frequency cones, but I just want to point people who weren't aware of that to a few directions where people are generating cones that have genuinely quantum properties. Okay, and usually these cones, for example, the microcone is generated via 4-wave mixing, where you take 2 photons and those photons break apart into single and Eigler photons. This is a fundamental quantum process. Other frequency cones can be generated with a single photon that breaks into 2 photons. So these are fundamental quantum processes. And colleague Olivier Pfister is doing this in below threshold OPOs, making things he calls cluster states. Another group that I'm aware of, led by folks out of Oak Ridge and Andy Weiner at Purdue, are implementing these types of entangled frequency cones using simple devices, actually, quite interesting, phase modulators and pulse shapers, to again build up technologies that could be useful for quantum processing. So I think these these directions are actually quite new. It's just results from the past couple of years, but I expect there will be more and more growth in this area. And right now, you know, the thing that is quite different about this than the classical frequency combs I described to you is these combs are not performing a fundamental quantum transduction, if you will, transducing a microwave photon to an optical photon, where you maintain say the quantum properties of that photon. Here they're more using just the photons or the cone structure as bins that can be entangled and can be used for different types of processing or quantum information processing. So it's, I wouldn't want people to be confused that frequency combs, quantum frequency combs are performing a measurement analogous to, say, the work that Conrad Leonard and Cindy Riegel have done here of really quantum transduction between the microwave and the optical, which is a very hard problem. If one could do that with a frequency comb, that would be spectacular, but I don't see that as something on the horizon right away. How I see frequency combs entering the quantum regime is a bit more like the LIGO model, I would say, is that, you know, the LIGO model is one, it was a hard path, right? But basically the LIGO model was, well, let's keep turning up the power until we can't turn up the power anymore, and then we got to figure out a way to turn down the noise. And so it was only in the past handful of years that LIGO introduced squeezed vacuum into the interferometer to reduce the noise at a level so that their signal to noise was significantly larger, so that they could make more sensitive measurements of gravity waves. So in measurements that I'm involved in, where this first came to us is in this process called optical frequency division. This is work that actually started here at Gilla, but I worked on for a decade with Leo Holberg, and then more recently with Tara Fortier and Frank Quinlan. And the idea is to start with one of these very stable optical oscillators, produces a pure sine wave in the optical domain, use a frequency cone to divide it down, photodetect the pulses hitting the frequency cone, and that would give you, say, a microwave signal at 10 gigahertz. This has produced the lowest noise microwaves ever generated. And here's a few examples. This is a metric that we use, a phase noise power spectral density. But maybe like a takeaway number is up here on the right, is that the curve, the integrated power on one of these curves, the colored curves, is about a few femtoseconds, so less than the cycle of light. Whereas the very best microwave oscillators are a couple orders of magnitude above that. So the integrated timing jitter or the noise on this optical frequency division process can be extremely low. What we found, though, when we did this is that we were looking carefully at the noise at the highest offset frequencies, where you would come down to the shot noise. And together with Frank and Tara, what we observed was that actually the noise did not behave like shot noise, like we thought shot noise should. And that was because the noise process is different. It's something that's called cyclostationary. And that means that you don't have any noise when you don't have photons on the detector. The photons come in pulses, okay? And then when the photon's there, there's noise, there's shot noise on the photons. But in between, there's nothing. And so this leads to an imbalance in amplitude and phase noise between the two quadratures. And a simple cartoon is shown here, where blue is a longer pulse, red is a shorter pulse. And you can see that the noise can be concentrated kind of in shorter bursts. And if you look in the one quadrature, where say this timing reference crosses 0, the integrated noise on the short pulse is significantly less than the noise on the longer pulse. And this was an idea, actually, it came out of the gravity wave community. Tim Niebauer was a student who worked with Jim Fowler here, and they made some of these observations with gravity wave community in Germany for amplitude modulated light. But what that allowed us to do is push the shot noise floor of these microwave signals down by about 5 dB by using shorter optical pulses. It seems simple now, but it was actually a surprising observation to us at that point. So I think there's an opportunity there, there's a lesson there, is that as we look for ways to improve the signal to noise, it might just be right in front of us, and we just need to understand it and figure out how to make it useful. I told you a little bit earlier about, about the way we measure these electric fields, sampling the electric fields. And this device that we use was short pulses that were mixed with the infrared pulses and kind of like a digital sampler measuring the waveform. So this is an actual movie from the lab. I'm showing you our 100 terahertz sampling oscilloscope. Okay, that's a waveform there that has a frequency of about 100 terahertz, or actually it's about 60 terahertz, and it's being sampled by these very short delta function frequency cone pulses. We do that in this kind of balanced polarimeter down here, balanced detection. So we've been doing that for several years, and we started looking at that more closely. And we found that if we take many of those measurements and average them, thousands of them, we get signals that look like this. And we wanted to ask ourselves, well, what's the limit? How well can we measure maybe the amplitude? And so here's one of those signals, and above is just a zoom in on one cycle. How well can we measure the amplitude, and how well can we measure the phase? And right now we're shock noise limited at kind of the 1 femtosecond level. But at the same time, there were some very kind of interesting and provocative results that came out of a group in Germany, where they claimed they could see sub-cycle squeezing and anti-squeezing on such waveforms. And these waveforms are generated in a quantum process, parametric down conversion. And so it is plausible that there could be something like that. And that's an area that we realized that we didn't actually even know how to describe that mathematically. So we enlisted a new colleague here, Josh Coombs, who I've really enjoyed interacting with mostly over Zoom for the past year, but now a few times face to face. And right now we're pushing to see if we can understand answers to these questions. And that is, what's a full quantum description of this measurement system here? You see, it looks like balanced detection. It's a balanced heterodyne detector. And can we apply this to non-classical states of light? And could that ultimately lead to enhanced sensitivity, some sort of tomographic measurement of electric fields, very fast electric fields, that could be used to improve not only the zero crossing, our knowledge of the timing precision, but also the amplitude. I just got a few more slides, so I know we're coming to the end here, and I'm a little bit over. This was another one is we asked ourselves, could we use that to look at other types of light? Could we sample not just coherent states or non-classical states, squeeze states, but original quantum light, thermal light? And we've been doing this recently in kind of a simple way, and I'll not be able to spend much time on it, but I wanted to emphasize one thing that I learned recently that I really like in this measurement is that if we collect light from the sun and do measurements on a solar line there's an iron line in the sun, we can be within about 20% of the quantum limit. What that means that in this optical node, which we're collecting in a fiber coming from the sun, 80% of the photons make it to our detector, all the way from the sun to our detector, are heterodyne with the local oscillator laser, and agree exactly with the formula that we'd expect for the signal to noise. And the average photon number here is the photon number, the Bose-Einstein distribution of photons in that node. So it seems to me that there's some interesting lesson there, that we can really make measurements at the limit of quantum mechanics on thermal sources as well. My last slide is something that I won't do justice to, but it's again an idea working on together with Josh Coombs that I just wanted to throw out here and present to the first snapshot of. And that's appropriately named for Josh, Homodyne. And could this be a new metrology tool? So people are familiar with homodyne and heterodyne, where there might be a signal of interest in a local oscillator, and that produces these measurement pictures, phasor diagrams of stick with an uncertainty ball at the end of that. And the Wigner function of that kind of measurement, or that state, the coherent state, looks like that. The idea with homodyne is that we're going to send in a local oscillator as a comb and not a coherent state. And of course, a comb is a type of coherent state. But what we expect is that we don't just get one dot in this phase space, but we get multiple dots. And it's very early, but I think there's some possibility that this key point can be realized. And that is, we can sacrifice something about which interval or which dot we're looking at here in order to gain knowledge about where in the interval. So that's exactly how it works with the frequency comb. If you interfere CW light with a comb, you get heterodyne with every comb tooth. So it's some idea analogous to this, that we're gonna not know which cone tooth there's ambiguity in the cone tooth that it's interfering with, but that could lead to a knowledge of reduced uncertainty in the exact interval. So I think with that, I'll quickly stop here and wrap up because there's going to be other folks coming in the door. I need to give a huge thank you to many people, my NIST colleagues. And this is a big list, inclusive list, but in particular, like Scott and Frank and Tara, were people I've worked on these problems for many years. And more recently, the group of students and postdocs I'm working with. And some of you know that next year I'm going to be moving across the street to make my headquarters here at the University of Colorado. And if there's new students or postdocs looking for a place to hang out, I'd be happy to talk with you. So, thank you for your attention.
As Scott mentioned, we have to be out of here in a few minutes. It's a beautiful space and other people want to use beautiful space, but
It's my strategy to not give time for hard questions.
we have time for one or two extremely tough questions.
Sure. Yeah.
I'm interested in cone spectroscopy, molecular spectroscopy. You said you can see the fingerprint of molecule, but I feel like since cone has a lot of colors, someone kind of transition or many things like effects, so it is not necessarily same to the single frequency spectroscopy. So I feel like how people do it.
Yeah, I think the picture I gave, that, so the question was, with frequency cone spectroscopy, you have lots of cone teeth. What about processes like Raman, or maybe if I'm understanding that you would drive some nonlinear transition with two cone teeth, and so it could get kind of confusing. So that absolutely does exist. I would say that the examples I gave were linear spectroscopy, just linear absorption. So with low intensities, so as to not drive these Raman processes. We have done frequency cone spectroscopy again at low powers, where we would measure, say, multi-step transitions. But I guess to your question is that, yes, it could get confusing if you put high intensity on the sample, but in general, we aren't doing that. Although there could be very good reasons to do that.
You said cone is very high frequency because high intensity because in time domain is very short time.
Yeah.
But I mean, so the frequency but it's low.
Yeah, so I guess the question was, the follow-on was, well, isn't don't we have really high intensity in the time domain? It sounds like it's unavoidable to have nonlinearities. You know, and that's true, but in many spectroscopic scenarios, we maybe even let the pulse stretch out. But yeah, these are things that it's not too hard to take care of to make sure that you aren't driving nonlinear processes.
So let's thank Scott one more time.